Hello everyone, and thanks for watching Edupedia World Videos. This is the third and final video for the topic of capacitors, and in this we'll consider some advanced concepts for which capacitors are generally used. The first thing we would like to calculate is the force between the plates of a capacitor. And for all these cases we'll assume that it's a parallel plate capacitor, but since you know how to derive the capacitance of both a parallel plate capacitor and a spherical capacitor or cylindrical capacitor, those particular problems should not cause you much difficulty. In a parallel plate capacitor, let's say this plate has a charge Q, this plate has a charge minus Q, both of them have area A, the distance between them is D. This particular sheet has an electric field of sigma by 2 epsilon naught, and this particular sheet also has an electric field of sigma by 2 epsilon naught, which leads to a total net electric field of sigma by epsilon naught going from the positive plate to the negative plate. But if we want to see the force with which the positive plate attracts the negative plate, then we only need one sigma by 2 epsilon naught. After all, a charge kept at some position will never attract a force on its will never apply a force on itself. If there are two charges and you need to find out the force between two charges, you need to find out the force by this charge on this charge, and for that you will calculate the electric field due to this charge only, right? So the electric field is sigma by 2 epsilon naught, and if a small area here, let's say A dash, has a charge sigma A dash, then the force it will feel will be Q times the electric field. That means sigma A dash into sigma by 2 epsilon naught. Or we can say that the force per unit area, F by A dash, is equal to sigma square by 2 epsilon naught. So that means the force between the plates of a parallel plate capacitor is sigma squared by 2 epsilon naught, but this is the force per unit area. If you want to find out the actual force between the two, you just multiply it by area, and the answer you will get is sigma square A by 2 epsilon naught, or another way of writing that would be Q square by 2A epsilon naught. And since one plate is always positive and the other is always negative, they will always attract each other. The next concept would be the energy stored inside a capacitor. So for that, what we'll need to find out is what is the work done in creating a capacitor. So let's say we have a single plate with no charge on it, and instead we start splitting it into two small plates and give equal and opposite charges on all of them. Right now they're very close to each other, and we start pulling them apart. We keep one plate stationary and we pull apart the second plate until it is at a distance d away. So the amount of work we will have done will be F times D, where F is the force between the two plates, because the force will be constant, we saw that previously, and it will be in the direction towards attraction. So we'll have to apply a force in the opposite direction, and F dot D will be the total amount of work done by us. That will be equal to Q square by 2A epsilon naught D. If this is the amount of work done to create this capacitor, this is also the energy stored in the capacitor. But this is not always the quantity of interest, and a quantity which is generally of more interest is the energy per unit volume. And if you wanted to calculate the energy per unit volume, that would be Q square D by 2A epsilon naught divided by the volume, which would be AD. So A squared and D would cancel. That would give me sigma squared by 2 epsilon naught, which would be equal to half epsilon naught E squared, because E is equal to sigma by epsilon naught, the electric field between them, right? And this actually gives us a result which is not only true for capacitors but is true everywhere in electrostatics, mind you, not electrodynamics, and that is that the energy per unit volume due to any electric field is half epsilon naught E squared. It is also called the energy density. So if there is a region in which you have an electric field of E, then there is an energy per unit volume or energy density called which is equal to half epsilon naught E square. Right? And this is what we mean by saying that energy stored in the capacitor, it is stored within this volume, because the total energy is half epsilon naught E square multiplied by this volume. Next let's look at what I mentioned we would look at eventually, that is what happens when two plates of a capacitor are not given equal and opposite charges. So in this case we'll have to view the plates as objects of extended thickness, because that's really what they are. Let's say we give this a charge of Q1 and this a charge of Q2. Right? Now first of all we'll create a Gaussian surface like this, and we know that the electric field has to be in the horizontal direction, so the curved surface does not have any flux through it, and since the flat parts are within the material of the conductor, they will not have any electric field through them as well, or electric flux. So that means that the total charge enclosed in this Gaussian surface is 0. That means if this side, and this is true for any area A, so this might be true for the whole plate as well. So if this surface has a charge of Q, then this surface has to have a charge of minus Q. Now if this surface has a charge of Q, then the leftover charge must go to the left surface, and that will be Q1 minus Q. And here the charge will be Q2 plus Q. Right? So now we have one unknown Q. As soon as we find Q, we'll be able to find everything. But another thing that needs to happen for the electric field at this point to be 0 is that the electric field due to this surface is towards the left, due to this surface. The electric field due to this surface is towards the right, and they cancel each other. Right? But if you look at the other two surfaces and you assume that there are positive charges on both the surfaces, the electric field due to this surface will be towards the right, and the electric field due to this surface will be towards the left, and they both must add up to 0 as well, because the electric field within the material of a conductor has to be 0. And what that gives me is these two plates have to have equal charges, not equal and opposite, equal charges. Right? If two plates have equal charges, then the electric field between them is 0. Right? So if they have equal and opposite charges, then there is an electric field between them, and electric field outside them is 0. So the equation we get is Q1 minus Q is equal to Q2 plus Q, or Q is equal to Q1 minus Q2 by 2. We assume that Q1 is greater than Q2. If not, this would be the negatively charged plate. But ultimately, Q is equal to Q1 minus Q2, and Q1 minus Q will be Q1 plus Q2 by 2. Right? So the outer two surfaces will actually have a charge of Q1 plus Q2 by 2 each. That means the total charge will split up, and half will be divided on each of the outer surfaces, and the inner surfaces will have equal and opposite charges. So if we were to calculate anything related to the capacitance, Q will have to be taken to be Q1 minus Q2 by 2, because these are the only surfaces which will create an electric field inside, and a capacitance has to do with the electric field inside. That's why there's an energy stored, that's why there's work done. So Q1 plus Q2 by 2 on both sides will not give any net electric field in this region, because they'll be equal and opposite. But Qn minus Q will have the same direction of electric field in this region, and this is the Q which we'll use whenever we're calculating something related to capacitance. A few other concepts left in this chapter are concepts of corona discharge, and that happens when you have a conductor of varying radius, or of varying surface radius would be the better word. So let's start by looking at two conductors of different radii. Let's say this has a radius R1, this has a radius R2, this has a charge Q1, this has a charge Q2. If they are connected by a conducting wire, then they have to be at the same potential. That means Q1, actually let's call this R1 and let's call this R2 for the sake of symmetry. Q1 by 4 pi epsilon naught R1 is equal to Q2 by 4 pi epsilon naught R2. Right? What is sigma? Sigma is Q by R squared. So if you divide by R once again, then what you will get is basically sigma 1 R1 is equal to sigma 2 R2. That means the sphere with the smaller radius has the greater sigma. A greater surface charge density exists on the sphere of smaller radius. Let's extend this concept to a single conductor which does not have any specific shape. Now there will be regions like this which can be assumed to be parts of spheres which have a very large radius, like this, right? So these regions which have large radius or can be assumed to have large radius will have small surface charge densities, as opposed to that these regions which look like the surface of a smaller sphere which have a small radius will actually have larger surface charge density. So this is what generally happens in an irregular conductor. Pointed ends or ends which have a small radius of curvature end up having high surface charge densities, and this can go to the extreme where if you have an end which is a point like this, then at this point it will have an extremely large surface charge density, and sometimes it might have such a large surface charge density that it might actually break down the air around it. Every material, we'll see this in the next video in detail when we talk about dielectrics, but every material has a electric field at which its dielectric properties break down and all the charges become free, and that maximum electric field is called the dielectric strength. And sometimes the charge might be so much that it might create a field which is greater than the dielectric strength of air, which means that the air gets electrolyzed and leads to sparks, which is called corona discharge. And you might have sometimes seen this in documentaries or movies when people are traveling along the Arctics, where you have magnetic particles driven in through the aurora borealis or the northern lights and the northern winds. In that case, if you have some pointed axe or something, then it's possible that the end of the axe might start creating sparks, simply because that is a conductor which has a pointed end, which results in it having an extremely large surface charge density in order for the whole conductor to be equipotential. This has a good application to create a large potential difference in something which is called the Van de Graaff generator. And what happens in this case is, I'll try to draw a rough diagram of this. So you have an outer sphere, and then you have an inner smaller sphere which is attached to another sphere through a conveyor belt. And near this end, there's obviously a stand here. You can look up the proper figure somewhere. Unfortunately, I don't have extremely high drawing skills when it comes to drawing on the tablet. There's a comb here and another end here. These are pointed ends, and these are kept at a small potential difference. And this is a conveyor belt which keeps moving. And there's another comb here. A comb just means a conductor with pointed ends. It's called a metallic comb generally. So when you have a conductor with a certain potential, then the air around these pointed ends will get highly charged, and what it will result in happening is the breakdown of air, which results in these positive charges being transferred to this belt. Right, that happens because these ends are pointed. Now this end is moving up and this end is down, so these positive charges will be taken to the top. At this point, again near this comb, dielectric breakdown will occur, and these positive charges will go to the comb, or to because if they're on the comb, they'll ultimately end up on this big sphere. So what this Van de Graaff generator does is, using this principle of corona discharge, it takes some charges at a small potential difference and transfers it to a sphere which might have a very large radius. As the radius of the sphere is very large, you need to have a lot of charge in it, and as you keep accumulating charge on the sphere, the potential on the sphere increases. And this is a way to create a very large potential difference from a very small potential difference by simply transferring charge from a small sphere to a large sphere. There is a limitation in the Van de Graaff generator. Sometimes you can get so much charges on the surface that they themselves result in the dielectric breakdown of air. So that is the limitation. You can only create potential differences slightly smaller than those which might result in the breakdown of air. Right. But other than that, you can have a small potential difference and use it to create a very large potential difference using this concept of corona discharge. This completes capacitors. This completes simple capacitors. In the next video, we'll see what happens when we start inserting dielectrics or a particular type of insulator into capacitors, and it changes the behavior of capacitors drastically. Thank you.